Dear students, welcome for our lecture series on agrochemicals and pest control. We are going to deal with the topic analysis of agrochemicals. India is primarily an agriculture based country. The agricultural sector and its other associated spheres provide employment to a large section of the country's population and contribute about 25% to the gross domestic product. Agrochemicals are those chemicals which are used to improve the productivity of crops by improving fertility of soil and protecting them against pests. Primarily, agrochemicals are classified as fertilizers and pesticides. Fertilizers such as synthetic fertilizers, hormones, chemical growth agents, raw animal manure and pesticides such as insecticides, herbicides, fungicides from the agrochemical market. Balanced nutrition is a base of high yield, but frequently agronomist identifies plants need in some fertilizers using only outward signs by sight. This method is not reliable because outward signs of deficiency of different nutrients are similar and even experienced agronomists can make mistake. Thus, in this episode, the following aspects are going to be seen. They are sample preparation by chromatographic techniques, application of radioisotopes in agriculture, polarography and fluorescence spectrophotometry, ultraviolet visible spectroscopy and infrared spectroscopy, and nuclear magnetic resonance spectroscopy and mass spectrometry. Coming to the first one, sample preparation by chromatographic techniques. Food samples present an enormous challenge to analytical chemists in their efforts to determine residues of pesticides at trace levels to satisfy food safety regulations in EU, USA and Japan. The wide array of food matrices from liquids to solids require different sample preparation techniques for accurate and reproducible results with chromatographic techniques such as gas chromatography and high performance liquid chromatography. In addition, there exists a wide range of pesticides which are used legally for crop protection and their residue content in food must be accurately monitored for safe consumption. The GC and HPLC techniques with different types of detector systems can provide such analysis at trace levels to fulfill the maximum residue levels as per the food safety regulations in these countries. However, the accurate and reproducible results often depend upon the sample preparation techniques associated with the different food matrices. Sample preparation has always been regarded as the bottleneck in the analytical laboratory performing numerous analyses, but it is the key to accurate analysis. In this regard, as per pesticide residue analysis, where not only the physical volume of the analysis can be enormous, but also the number of pesticides involved can range from a selected few to a broad spectrum depending on the food source. This will usually necessitate the employment of different sample preparation methods for different targeted pesticides as well as the multitude of food matrices. It has been estimated that the sample preparation step in most determinations consume approximately 60 to 70% of the total time required for the analysis. It must be able to produce analytically accurate results and be economically efficient for routine analysis. In addition, it must be safe and easy to perform. More sample preparation procedures for GC and HPLC determination follow the basic steps as outlined below. The food sample is homogenized or blended to obtain a uniform matrix. This will be followed by extraction of the pesticide residue with solvents. A cleanup step is employed to remove interfering matrix components from the GC or HPLC chromatograms. The elution or fractionation of the extracted analytes. Concentrate the eluent and reconstitute in a solvent which is compatible with the GC or HPLC conditions. Finally, the solution containing pesticide can be introduced into the GC or HPLC. Moving on to the next, applications of radioisotopes in agriculture. Radioactive materials are used in a wide variety of applications in everyday life. Research laboratories, medical centers, industrial facilities, food irradiation plants and many consumer products all use or contain radioisotopes. Radiation is used to kill bacteria, molds and other microorganisms in strawberries, onions, potatoes, meats and spices, preventing the food from spoiling and making it safer to eat. Radioisotopes decay by emission of radiation and energy they possess can be utilized in wide range of agricultural applications. Nuclear scientists and technologists are unlocking the secret of many agricultural problems which could not have been possible with conventional methods. Radioisotopes were used for producing high yielding crop seeds to increase the agricultural yield. Radioisotopes were also used for determining the function of fertilizers in different plants. Radiations from certain radioisotopes were also used for killing insects which damage the food grains. Fruits, vegetables and canned food can be stored for longer periods by gently exposing them to radiations. Applications of radioisotopes and radiations are helping us to find the solution of problems in much shorter time. The production of radioisotopes by nuclear reactors and other atomic installations have increased the use of radioisotopes in the field of agriculture. India is leading producer of radioisotopes in the world and our nuclear scientists are engaged in developing various technologies for the beneficial uses of radioisotopes. Now coming to polarography and fluorescence spectrophotometry. First one, polarography. Polarography, also called polarographic analysis or voltammetry in analytic chemistry, an electrochemical method of analyzing solutions of reducible or oxidizable substances. It was invented by Czech chemist Jaroslav Hryvorský in 1922. In general, polarography is a technique in which electric potential or voltage is varied in a regular manner between two sets of electrodes while the current is monitored. The shape of polarigram depends on the method of analysis selected, the type of indicator electrode used and the potential ramp that is applied. The potential ramps are applied to a mercury indicator electrode and the shapes of resulting polarograms are compared. The majority of the chemical elements can be identified by polarographic analysis and the method is applicable to the analysis of alloys and to various inorganic compounds. Polarography is also used to identify numerous types of organic compounds and to study chemical equilibrium and rates of reactions in solutions. When the solution contains several substances that are reduced or oxidized at different voltages, the current voltage curve shows a separate current increase and limiting current from each. The method is thus useful in detecting and determining several substances simultaneously and is applicable to relatively small concentrations. Next, fluorescence spectrophotometry. Fluorescence spectrophotometry is the measurement of the fluorescence, that is, photoluminescence emitted by a substance while it is being exposed to ultraviolet, visible or other electromagnetic radiation. In general, the light emitted by fluorescent solutions is of maximum intensity at a wavelength longer than that of the absorption band, causing excitation usually by some 20 or 30 nanometer. The intensity of the light emitted by a fluorescent solution is in certain circumstances a simple function of the concentration of the solute and can therefore be used for analysis. It is difficult, but to measure absolute fluorescence intensity, and measurements are usually made by reference to dilutions of a properly selected reference substance. The general scheme in fluorescence spectroscopy is therefore to stimulate with radiation at the wavelength of maximum absorption and to measure or compare the intensity of the fluorescent light with that of the reference solution. The fluorescent light should be carefully freed from scattered incident light. Regarding the apparatus, measurement of fluorescence intensity can be made with a simple filter fluorimeter. Such an instrument consists of a radiation source, a primary filter, a sample chamber, a secondary filter and a fluorescence detection system. In most such fluorimeters, the detector is placed on an axis at 90 degree from that of the incident beam. This right angle geometry permits the incident radiation to pass through the test solution without contaminating the output signal received by the fluorescence detector. However, the detector unavoidably receives some of the incident radiation as a result of the inherent scattering properties of the solutions themselves or if dust or other solids are present. Filters are used to eliminate this residual scatter. The primary filter selects short wavelength radiation capable of causing excitation of the test substance, while the secondary filter is normally a sharp cut off filter that allows the longer wavelength fluorescence to be transmitted but blocks the scattered radiation. The cells used in fluorescence measurements may be rectangular cells similar to those used in absorption spectrophotometers, except that they are polished on all four vertical sides and on the bottom, or cells in the shape of round tubes with flat polished bottoms may be used. Calibration of the wavelength scale. The wavelength scale of the fluorescence spectrophotometer should be periodically calibrated. Coming to preparation of solution. The solvent used for the measurement should be properly selected. The solvent itself, its purity and its pH may markedly affect the intensity and spectral distribution of fluorescence. Test solution prepared for fluorescence spectrophotometry are usually 10 times to 100 times less concentrated than those used in absorption spectrophotometry. In analytical applications, it is necessary that the fluorescence intensity be linearly related to the concentration in the range used for measurements. But if a solution is too concentrated, a significant part of the incident light is absorbed by the substance near the cell surface, thus resulting in a reduction of the light reaching the center. That is, the substance itself acts as an inner filter. Fortunately, fluorescence spectrophotometry is inherently a very sensitive technique and concentrations of 10.5 to 10.7 moles per liter are frequently used. Regarding the measurement technique, fluorescence measurements are sensitive to the presence of solid particles in the test solution. Such impurities may reduce the intensity of the exciting beam or give misleadingly high readings because of multiple reflections in the cell. It is therefore wise to eliminate solid particles by centrifugation. Filtration may also be used, but some filter papers may contain fluorescent impurities. Oxygen dissolved in the solvent has a strong quenching effect. The intensity of fluorescence is therefore increased by use of a degassing procedure such as bubbling nitrogen or other inert gas through the test solution. Temperature regulation is often important in fluorescence spectrophotometry. For some substances, fluorescence efficiency may be reduced by as much as 1 to 2% per degree of temperature rise. In such cases, if maximum precision is desired, temperature controlled sample cells are essential. For routine analysis, it may be sufficient to make measurements rapidly enough so that the test solution does not heat up appreciably from exposure to the intense light source. Many fluorescent compounds are light sensitive. Exposed in a fluorescence spectrophotometer, they may be photodegraded into more or less fluorescent products. Such effects may be detected by observing the detector response in relation to time and may be reduced by attenuating the light source with filters or screens. Now coming to ultraviolet visible spectroscopy and infrared spectroscopy. First one is ultraviolet visible spectroscopy. Ultraviolet visible spectroscopy or ultraviolet visible spectrophotometry refers to absorption spectroscopy or reflectance spectroscopy in the ultraviolet visible spectral region. This means it uses light in the visible and adjacent ranges. The absorption or reflectance in the visible range directly affects the perceived color of the chemicals involved. In this region of the electromagnetic spectrum, molecules undergo electronic transitions. This technique is complementary to fluorescence spectroscopy in that fluorescence deals with transitions from the excited state to the ground state, while absorption measures transitions from the ground state to the excited state. Molecules containing non-bonding electrons can absorb the energy in the form of ultraviolet or visible light to excite these electrons to higher anti-bonding molecular orbitals. The more easily excited, the longer the wavelength of light it can absorb. Next is infrared spectroscopy. Infrared spectroscopy is the analysis of infrared light interacting with a molecule. This can be analyzed in three ways by measuring absorption, emission and reflection. The main use of this technique is in organic and inorganic chemistry. It is used by chemists to determine functional groups in molecules. Infrared spectroscopy measures the vibrations of atoms, and based on this it is possible to determine the functional groups. Generally, stronger bonds and light atoms will vibrate at high stretching frequency. Moving on to the last part, nuclear magnetic resonance spectroscopy and mass spectrometry. Nuclear magnetic resonance spectroscopy. Nuclear magnetic resonance spectroscopy is an analytical chemistry technique used in quality control and research for determining the content and purity of a sample as well as its molecular structure. For example, NMR can quantitatively analyze mixtures containing known compounds. For unknown compounds, NMR can either be used to match against spectral libraries or to infer the basic structures directly. Once the basic structure is known, NMR can be used to determine molecular conformation in solution as well as studying physical properties at the molecular level such as conformational exchange, phase changes, solubility and diffusion. In order to achieve the desired result, a variety of NMR techniques are available. First one is mass spectrometry. Mass spectrometry is an analytical tool used for measuring the molecular mass of a sample. For large samples such as biomolecules, molecular masses can be measured to within an accuracy of 0.01% of the total molecular mass of the sample, that is within a 4 Dalton or atomic mass units error for a sample of 40,000 Daltons. This is sufficient to allow minor mass changes to be detected. Example, the substitution of one amino acid for another or a post-translational modification. For small organic molecules, the molecular mass can be measured to within an accuracy of 5 ppm or less, which is often sufficient to confirm the molecular formula of a compound and is also a standard requirement for publication in a chemical journal. Structural information can be generated using certain types of mass spectrometers, usually those with multiple analyzers, which are known as tandem mass spectrometers. This is achieved by fragmenting the sample inside the instrument and analyzing the products generated. This procedure is useful for the structural elucidation of organic compounds and for peptide or oligonucleotide sequencing. Mass spectrometers can be divided into 3 fundamental parts, namely the ionization source, the analyzer and the detector. The sample has to be introduced into the ionization source of the instrument. Once inside the ionization source, the sample molecules are ionized because ions are easier to manipulate than neutral molecules. These ions are extracted into the analyzer region of the mass spectrometer, where they are separated according to their mass to charge ratio. The separated ions are detected and this signal sent to a data system where mass to charge ratio are stored together with their relative abundance for presentation in the format of a mass to charge ratio spectrum. The analyzer and detector of the mass spectrometer and often the ionization source too are maintained under high vacuum to give the ions a reasonable chance of travelling from one end of the instrument to the other without any hindrance from air molecules. The entire operation of the mass spectrometer and often the sample introduction process also is under complete data system control on modern mass spectrometers. So now we can conclude this session. Pesticide contamination of foodstuffs has become a worldwide concern, prompting various levels of regulation and monitoring. Traditionally, pesticides are quantified with gas chromatography combined with selective detectors. Selective gas chromatography detectors are great tools to quantify one or two pesticide classes at a time. However, screening for a number of different pesticides require multiple runs utilizing various gas chromatography configurations. As a result, gas chromatography mass spectrometry has become a preferred technique for pesticide analysis because of its single run capability. Students, I wish you find some important information regarding the topic. Thank you so much for watching this session. We will meet in the future episode. Till then, take care.